How many of these are perfect squares? Okay, method one is to actually work each of them out. So 1 cubed is 1, just 1 times 1 times 1. 2 cubed is 8. And in fact, maybe a good start is to write down your cube numbers. 3 cubed is 3 times 3 gives 9, times 3 again is 27. And 4 cubed is 4 times 4, 16. Double it, 32, double again, 64. 5 cubed is then 5 times 5, 25, times by 5, 125. It's worth learning these, to be honest, so you can just very quickly write them down if possible. So now I can just add them. I'm going to get 9 for this one, which is a square, perfect square. And then if I add on 27 to that, this extra term, I'm going to get 36, which is 6 squared. Maybe I should just write these down as I go. So yeah, that one's okay. And then if I add 64 to 36, wow, we get 100, which is 10 squared. And then finally, if I add on 125, we get 225, which in fact is 15 squared. So all of them are perfect squares. Now, is this a coincidence? Does it work for other ones, you might be thinking? And the answer is yes, it will always work. Because if we maybe look at the pattern, we've got 1 cubed plus 2 cubed, which is equal to 3 cubed. But if we like separate it, it's actually equal to 1 plus 2, sorry, 3 squared over here. It's actually 1 plus 2 squared. So that 9 can be written as 1 plus 2 squared. Now let's just look at the next one. Does it follow the same pattern? I'm not saying it's easy to spot that, but it is true. Okay, the next one was 6 squared, so it's 1 plus 2 plus 3 squared. And it works, in fact, for all of them. Just write down one more. So this is actually equal to 1 plus 2 plus 3 plus 4 squared. And there is a result that says that 1 cubed plus 2 cubed all the way up to n cubed is equal to 1 plus 2 all the way up to n squared. It's a really lovely formula, in fact, that when you sum all the cubes, it's equal to the sum of just the integers, and then you square at the end. Now I'm going to delve a little bit more into what you need to know for this challenge, but I think it's quite interesting because it is possible to show that this sum here, 1 plus 2, and this can be useful, by the way, in math challenges and other areas. This is actually um, the formula for finding an nth triangle number, and it's a half n plus 1. In fact, I'm going to show you where it comes from. So let's say I want to add all these numbers together. And I'm going to call maybe the sum s. What I can do is rewrite it in the opposite order. Now, why would I do that? Because when I add them together, and I'm going to get two lots of the sum, I get n plus 1 here with this pair, and then I get n plus 1 here. And this one is also n plus 1. In fact, they're all n plus 1. You can hopefully convince yourself of that. And we've got n terms here, so it's going to be n lots of n plus 1, which means that 2s is equal to this, which gives that formula. Okay, we divide through by 2 to give s is equal to half n plus 1. Now, it's a little bit more complicated to derive the result for this one. It's possible. It's done in further maths at A level, but that shouldn't stop you having a look into it if you're interested. I'm not going to show it here, but what it will lead to basically is when I square my sum, I'm going to square each term separately. So I'm going to get a quarter times n squared times n plus 1 squared. And basically, that's what each of these are equal to. If you're convinced by my argument here, then you can hopefully be convinced that this on the right is this. And I'm just telling you that it is possible to derive it for the sum of the cubes as well. So that is the nth term of both. But returning back to this question, that's why it works. Yeah, really neat question.